Welcome to Windows on the World. This week we're going to be talking about the electric universe. Now, many people may have seen the film Thunderbolts of the Gods, and also a film called Fingerprints of the Gods, which goes into the ancient background of what this is all about. I'm with Steve Pank, and we're going to start by talking about the nature of electricity in the universe. So, Steve, welcome to Windows on the World.
Thank you.
Tell us a bit about this, the electricity, and what it really is.
Well, in 1752, Benjamin Franklin carried out an experiment in Philadelphia. He flew a kite in a thunderstorm. Attached to the string of that kite was a key which was hanging in a Leyden jar, which was an early form of electricity storage. As a result of this experiment, he was able to prove that lightning is electric. And he identified that electricity has two poles, a positive and a negative.
And this was just by observation of a thunderstorm. Now, what surprises me is that this hadn't been found out previously. So really, you're saying that it was Benjamin Franklin who first propounded this theory of what electricity actually is.
Well, there was a lot of very different theories at the time. Work had been done with static electricity, but it hadn't been followed through by scientists. It was mostly used by magicians as demonstrations to entertain people.
Right.
And these early magicians called themselves electricians.
Really?
But the only way you could really identify electricity was either by sparks or by shocks. Another interesting aspect was the electric eel, which had been known for thousands of years.
But it hadn't been known as the electric eel, obviously.
No. So, so that to bring that up to a bit more recently, up to the beginning of the 20th century, when people looked out into the sky, they thought that's all there was, stars and planets. But when these giant telescopes at Mount Wilson and later at Mount Palomar were built.
When was that?
I think, in the 20s for Mount Wilson and in the 40s and 50s for Mount Palomar, the astronomers discovered that we were actually in a galaxy called the Milky Way, but out there was millions or maybe even billions of galaxies which were as big as the Milky Way. And so they invented a new method of measurement, which they called the light year. Now, a light travels 6 trillion miles in 1 year. So just to give you an idea of the size of the universe that people had discovered, the nearest star is 4.5 light years away. The Milky Way is 500 light years across. And our nearest neighbouring galaxy is called the Andromeda Galaxy, is 2.5 million light years away. So that means that the light we're seeing now from the Andromeda Galaxy left Andromeda before the human race had even evolved.
Now, does this tie in with the theory of the expanding universe as well?
The thing about the expanding universe is it all depends on this phenomenon that they call the red shift.
Yeah.
And Edwin Hubble, who was the astronomer in charge of these two telescopes, Mount Wilson and Mount Palomar, noticed that some galaxies, the light was slightly redder than others. And there was some number of theories about this, but the one that really took hold was the fact that this actually meant that these galaxies were moving away. This has actually become the basis of astrophysics, that we're living in an expanding universe. But as far as the electric universe theory is concerned, the expanding universe theory creates a lot of problems. But the mathematicians who had followed Einstein's way of thinking have actually worked out that if the universe is expanding, then it must have actually started from somewhere, and they called this the Big Bang.
Oh yeah.
But those astronomers didn't take any account of the electricity that actually makes up the universe, and which is now increasingly being discovered by the probes and the radio telescopes that we now actually have. So the expanding universe theory does cause some problems. Essentially, they say, well, if it's expanding, it's increasing. It's expanding at an increasing rate. If it's expanding at an increasing rate, there must be a force that is causing that, and otherwise it contravenes the Newton's first law of motion, which is that anything expands being pushed by a force. So the astronomers, they've created this stuff called dark matter.
Yeah.
And they said, oh yeah, well this is because of the dark matter. We don't know what it is, but we know it must be there because otherwise our calculations don't work. And the other thing about it is that they work exclusively with gravity. They believe that gravity is what holds the universe together. Now, if it was just gravity, gravity only pulls things in one direction. The whole universe would end up eventually as one big blob, which it obviously hasn't done. So this is another thing they try and explain with this dark matter. And then
so in other words, dark matter is the implosion of matter into a greater density. Is that what it is?
No, dark matter is what stops that happening.
Right.
But they haven't taken account. They know the power of the electricity. They know that electricity is trillion times more powerful than gravity, and yet it doesn't appear in their calculations.
This is a problem, isn't it? Yeah. I can see where conventional science is starting to make huge assumptions that are probably, to me, even as a layperson, seem incorrect when I've studied this. And the electric universe theory and the way it's been explained to me does make sense. The other stuff seems rather woolly, and the idea of a Big Bang, I think, is for very childish minds. That's just my opinion.
Well, it goes back to a gentleman called Lemaitre, who was a Catholic priest, as well as being an astronomer. And he came up with the idea. Yeah. He presented it to Einstein, who threw it out of hand, rejected it completely. But when Einstein heard that Edwin Hubble had discovered the red shift and surmised that this could be caused by expanding, Einstein changed tack and changed his calculations to fit in, and then announced that this was his biggest mistake. But since then we've discovered quite a few other mistakes that Einstein's made.
Yeah, you can look on the internet for those. We won't go into those today. But so what we're going to talk about as well is atoms and what they really are.
Yeah, I'd like to talk about the basic principles of what atoms are and what electricity is. Because atoms are composed of three components, basically. They are protons, neutrons, and electrons. Now, neutrons don't have any charge. Protons have a positive charge, according to the allocation that was given them by Benjamin Franklin, and electrons have a negative charge. So this is what holds atoms together, is a positive and negative charge. Now, those electrons can be split off from atoms, but some materials exchange electrons very easily. Metals, for example. These are called conductors because electrons can flow through along atoms of metal. So that's why we use copper and aluminium and steel as conductors. Materials where they don't swap easily are called insulators. Now, if sometimes these atoms get broken up and you've got the electrons in one place and the protons or in another place, and of course they're always seeking to get back together, and this causes an electrical charge. This material is called plasma, and out in the universe they say that 95% of the material out there is actually plasma.
Now that makes complete sense to me.
Yeah.
That you've explained that, and that's basically the O-level physics, really, isn't it?
Yeah.
Or what was O-level
It
physics?
is, yeah.
Right? Now, that makes absolute sense. So why do people oppose this theory? There is opposition to this theory, isn't
Well, of course, it's particularly in this country, the establishment, the astrophysics establishment, they just deal with the mathematics of gravity, right? They're still back in the days when Newton ruled, and Einstein, who tweaked it using his Riemann geometry, and his idea that gravity bends space was seen as a great vision, you know. So Einstein has become he's become the avatar. He's become the great white light of physics, and thou shalt not dispute Einstein, despite the fact that Einstein himself disputed Einstein. But the thing about it is, what's interesting is, if you're studying this material, if you don't accept the Big Bang and you don't accept Einstein, you don't get your degree.
Of course not.
And you don't get your astrophysics degree. So there's a huge momentum, because everybody is trying to get a Nobel Prize. And every few weeks you get somebody else, an astrophysics graduate or a researcher, comes on the TV and presents their theory about how the universe works. There's nearly as many theories about how the universe works as there are stars in the sky. But for some reason, the electric universe people are being sidelined. I mean, they've met NASA and so on, and these people, but it's not really caught on. But what's changing things is the probes that they're sending out into space, looking at comets, and going out to the edge of the universe, circulating planets. All the information they're coming back with ties in with the electric universe theory. So one feels that the expanding universe, the Big Bang, dark matter, dark energy, and all the other paraphernalia that astrophysicists have come up with to pat up these theories seems to be getting decidedly rocky.
It's very interesting, isn't it? Yeah, because you've got, so is it Wallace Thornhill?
Yeah.
Yeah, I got familiar with his work quite a few years ago, and as we've said in this section, it starts to make sense, this stuff. We're going to go and talk a bit more about planets and the influence of planets in part two.
Yeah.
But that's a very, very interesting opener, Steve, and we're going to take a short break, and we'll see you in a couple of minutes. Welcome back to Windows on the World. We're talking about the electric universe with Steve Pank. We're now joined by Piers Corbyn, and we're going to carry on the discussion and progress into planets and the nature of plasma. So welcome back, Steve.
Thank you.
Now, just before the break, we were talking about electricity, and we're now going to go into the planets and how that comes into the electric universe theory.
Right. Well, of course, the nearest planet to the Sun is Mercury.
Yeah.
And it was discovered in the early part of the 20th century that there was an aberration in the orbit of Mercury. And Einstein's theory was based on this, and he claimed this was caused by gravity bending space, that it could be the gravity of the Sun. Now, the electric universe theory would look at the possibility that it was the electrical field around the Sun that was affecting this orbit as well. So this is something that needs to be looked into. If we move on, do you want to say anything about that?
Yeah, it's quite an interesting observation, this thing about it's about the precession of the orbit of Mercury, because it's not a complete circle, it's an oval, and that oval moves backwards, right?
But it's constant.
Well, it moves. It's not in the same orientation. It changes, right? Just like the orientation of the moon's orbit around the Earth changes, because that's another oval. And all these oval things that are orbiting in the solar system or the universe do generally precess and move backwards or forwards, depending on what's going on. But that's the basic idea. And as Steve said, there was these observations about the precession rate of the line of Mercury's orbit from the and closest to the most distant part from the Sun. It's perihelion and aphelion. And the Einstein's equations were able to explain a difference between what should be a precession rate due to the fact that the Sun isn't a sphere, and that causes certain things, and what's actually observed. Now, there were criticisms at the time, namely that what Einstein was looking to correct was actually a small amount in the differences between quite large numbers, and these are maybe the errors are in those large numbers, you see. And then of course we have an electric idea, which maybe there's going to be electric fields, which are, if the Sun is charged and Mercury is charged, then there will be extra electric forces. Now, I don't know how their calculations work out, but I mean, I think it's a fair thing to say that the way this is presented in standard physics in universities is grossly simplified, and the electric universe idea is another possibility. If you accept, you have to look at all possibilities around.
Yeah. So let's move on to
Sure.
to Venus. All right. Venus is often considered to be the sister planet to Earth, but in a lot of ways it's very different. The Russians a few years ago sent a probe to land on Venus. It lasted about 4 hours, because it's something like 500 degrees on the surface of Venus. It's a very hot planet. But the other thing is that what's come up now is the question of why isn't there any atmosphere on Venus? And they've discovered that there's such a huge electrical field around Venus that it would have driven off all the oxygen. Well, of course, Venus is often regarded as a sister planet to Earth. It's a similar size and it's next in the orbit. But there are considerable differences. When the Russians sent out a probe there, it landed and lasted about 3 hours because of the temperature. It's something like 500 degrees on the surface of Venus. You can see pictures of it. It's really hot. But it's still got an atmosphere. And one of the puzzles is, why isn't there any oxygen in this atmosphere? They've recently discovered that there's such a powerful electrical field around Venus that it's driven off. It's quite capable of having driven off all the oxygen. So that is evidence of the electrical effect that's had on the planet Venus.
Yeah, well, it was very interesting because when we looked at the work of Immanuel Velikovsky, he was completely derided for his predictions, which later turned out to be mainly true. So, are you saying that there was an atmosphere on Venus once, or they don't know?
Yeah,
No, there
what
isn't. You mean there was
planet.
oxygen on it once, I mean?
Yes, an atmosphere with oxygen. Yes.
Yeah, that's right. Well, of course, the astrophysicists, they're always looking for life, and they're always looking for atmosphere and where life exists. And they say, well, why isn't there any oxygen in Venus? And now they've discovered this electrical field is quite capable of driving off the oxygen.
Right. So
That's interesting, isn't it?
We've got unstructured mass, positive charge, plasma. We've got we've covered neutrons, protons, electrons, and basically the interaction of everything, which, as I said in the first part of the show, makes complete sense to me. So, Piers, where do you stand on the general theory of the electric universe?
Well, I think it is very important, and there's a number of things in standard physics which are not very well understood, which the electric universe appears to help in. So I'm fully behind it, although of course it's not a fully developed theory. I mean, there's two matters I would mention. One is about galaxies, and the other is about planets and so forth. So first of all, about the planets, I mean, ideas about atmospheres of planets are really, very important.
Yeah.
And if there's new ideas on them, they ought to be carefully looked at. However, the global warming theory means that the establishment do not want to look at the issue of atmospheres very much, because you see the reason why Venus is very warm at the surface, apart from being close to the sun, is it's got a huge atmosphere, and if the radiation equilibrium with the sun is at the top end of the atmosphere, which it will be if it's got a lot of dirt or black stuff or soot or anything in it, if it's opaque.
So this is the atmosphere that contains no oxygen, basically.
It doesn't know, the fact it's got no oxygen is relevant, but the point is it's a very big atmosphere.
Yeah.
So when you go down in the atmosphere, it has to get warmer, just like on the Earth. As you go up, it gets colder because of expansion and the motion of particles under gravitational fields, which is, gravity works okay there. So that's why the surface of Venus is very hot. Now, once upon a time, there was more atmosphere on the Earth, so the surface would have been warmer, you see, apart from other cooling effects through plants or whatever. But you see, the idea that the amount of atmosphere on a planet is the basic in terms of geological time definer of the surface temperature is a complete anathema to the global warmers who want to explain everything in terms of carbon dioxide. And I've had quite heated arguments with people that got involved in CO2 gobbledygook, who were really upset at the idea that the Earth could have had more atmosphere on it. Well, obviously the Earth must have had more atmosphere in the past, because the atmosphere has always been lost into space. I mean, it comes out of the ground, but the faster molecules shoot off, you see. So that is something that is not studied enough. Now, at our conference happening on the 8th and 9th of September, the New Dawn of Truth conference, which you can find about on our website or on the websites that we've mentioned before.
It was mentioned on last week's show, yeah.
Ned and Carl from America are going to be there talking about the theory of temperature surface of planets based on the amount of atmosphere in them, and they've got some superb calculations which bear it all out.
Well, we should be able to film that and put that out.
Absolutely,
Really
that should be discussed.
Yeah.
And the other thing I would say, and this is more important really from the point of view of electric universe, is the is galaxy formation, which Steve was talking about.
Well, let's just go a bit more about planets. Yeah.
Oh, you want to do more about planets first?
Yeah.
Yeah, we're going to do that in this section. So,
all right.
I mean, we're going to talk about Saturn.
So let's talk
Pluto,
about the
Mars,
Earth. Let's move on to the Earth, which I know you know a lot about.
We'll
You've been
do
already
galaxies
talking
later.
about,
Absolutely.
And
So we're going to talk now about our planet, the Earth.
yeah, our planet. Yeah, that's right.
Okay.
And this is where we come to Christian Birkeland, right?
Okay.
Who was a Norwegian scientist and explorer, and he went up to the north inside the polar circle, and in order to explore the nature of the aurora borealis, and he discovered that this was caused by electric currents coming from the sun to the Earth, and of course this was debunked by a lot of his contemporaries, but he has subsequently been proved to be true. And in actual fact, he could reproduce the effect of the aurora borealis in conferences and to an audience in halls. We're using a piece of equipment
in the lab,
called the Torella.
Demonstration.
Yeah, and in public. Yeah.
Oh, okay.
So that was interesting, and has been proved to be true. So I mean, you know quite a bit about the electricity in the southern in the upper atmosphere of the jet stream, don't you?
Yes, absolutely. Well, it's definitely the case that the electrical nature of the atmosphere is understudied. I mean, for a start, a lot of things about thunderstorms are not understood. A lot of things about the rate at which which raindrops form is not adequately explained by standard collision theories, and even involving some electricity. And the nature of tornado formation isn't well understood, and there's certain electrical effects that are definitely going on there, and there's a whole lot of non-study but of obvious electrical importance of the atmosphere beyond the troposphere, i.e. into the stratosphere and beyond, where there's a lot of ionized material and so forth, and all of that, of course, is run by electrical equations. So you cannot explain this stuff just by gravity. Now, of course, most scientists know that you can't use gravity alone, but the electric universe theory is really a bit more than that. It's about there's more fundamental things going on, which are blotted out by current thinking.
Yes.
I mean, how is it that hundreds of tons of water are supported up in the atmosphere and we see it travelling past as clouds?
Mm-hmm.
The answer is it's held there by the electrical field that's in the universe, in the atmosphere. And then, of course, if that electrical field changes, it's precipitated, it falls as rain.
How does that happen? Can you explain to people out there who might not know how that happens?
Well, I can explain that when we hear the weather forecast, they talk about atmospheric pressure and they talk about wind speed. Yes. They never talk about the electric charge, which actually has much more influence on the weather than the other things. They talk about isobars and cold fronts and warm fronts, but this is all...
Well, they'll give you a circulation pattern.
Yeah, the amount of electric charge and the ionization in the atmosphere is absolutely crucial to the behaviour of the weather. And you can see that the patterns from space are circular. It's very similar to the formation of galaxies.
Yes, those are the impressions that we see on the weather forecast, and Piers is obviously a weather forecaster, and his forecasts are quite accurate. So this is all stuff you must be quite familiar with. Do you take into account the amount of electric charge in the atmosphere, for instance?
Well, yes and no. I mean, basically clouds will form when water vapour condenses, but what sets off the water vapour condensing is more of a question. Now, once it's condensed, it will tend to fall down because they're heavier than the air around them. But it's very clear from our studies that when we have what we call red weather periods, which is periods where there's more activity from the sun affecting the planet, and there's more geomagnetic activity, which is the wobbles in the Earth's magnetic field. And those periods, which we can predict and define, R5 is the most active and R4 is the next one down. When you've got an R5 or R4 or even an R3, then you will get more rain formation, more thunderstorms, more severe tornadoes, and more formation of tropical storms than standard meteorology will expect. And in fact, our observations show that all, or nearly all, of the biggest tropical storms, without exception, or I haven't found any exceptions, without exception, form in these R5 or R4 periods.
That's really good, and a great place to leave it for this section.
Definitely connected with electricity.
Thank you very much, Piers. We'll see you in a couple of minutes. Welcome back to Windows on the World. We're talking about the electric universe. I've got Steve Pank, and we've also got Piers Corbin in the studio, and we're going to talk about electricity, negative, positive ionization, and over to you, Steve.
Right, yes. You probably remember in the 70s that ionizers became quite popular and people were having these things in their house because they were negative ions were supposed to be beneficial. Well, I studied this, and the book I read, the gentleman who'd written it had he'd gone to Geneva to work, and he got very ill, and he didn't know why. And he traced this and went to various specialists. He wound up going to a specialist in Israel who said, well, you're suffering positive ions. There's a wind there that is actually affecting your health. And there is apparently a similar one in Jerusalem. And various places in the world, there are these positive ion winds that affect people, and it affects people's behaviour. In some places, where this happens, they even take account of the fact that crime rate goes up when this wind is blowing. So this comes right back to the negative and positive charge in the individual atoms and the plasma effect in our own atmosphere. So out in space, there is a lot of ionization. Of course, we know as we go beyond, there's the ionosphere, and then there are these currents that astronauts have to go through to get to the moon. These, what are they called? Belts.
Van Allen belts.
Van Allen belts,
Yes.
Yeah, that's right, yeah. Well, apparently they researched astronauts, and a lot of the ones who went to the moon have suffered from a condition that would be created by radiation. So these currents are out there, but to go on to Piers was interested in Birkeland currents.
Yeah, that's
Now-
right. We talked about that.
Well, just
before.
orbiting the Earth
Yeah.
will going to get more radiation anyway.
Yeah, you will.
So
do,
it's,
yeah.
you don't need to go to the moon to get sick from radiation. I would have
Well,
thought you just
it wasn't going
go
to
in
the
a
moon,
satellite.
it was going through the moon, through the Van Allen belt.
That's another story altogether.
You mean
isn't
through
it?
the Van Allen belt?
Yeah.
Yeah, okay. But
That's right.
being on the space station, they're going to get
Well,
radiation sickness as well. I
the
would have
space
thought.
station doesn't actually
No,
reach.
it don't, indeed
Van
not.
Allen-
It doesn't
Van
go.
Allen
It's
belt.
not very high at all. No, that's a good point.
A couple of miles up, isn't it?
Right. Well,
Yeah. Okay. So yeah, but we're getting really to the nuts and bolts of of what the electric universe actually is here. And just before the break, we were talking about Birkeland currents. Can you explain
Right.
to us what that is, Steve?
Yeah. Birkeland electricity has certain qualities. One of the things is that once it's going, it'll continue to travel unless it's stopped by something. But out in space, there isn't anything to stop it. And when you're dealing with electricity, you've got four forces. You've got negative, positive electric currents, and you've also got magnetism, north and south pole. Now, whenever you get an electric current, you always have a magnetic field. And these magnetic fields form in a circular form around the current. So all this electricity we've got in this room or in the room that houses at home, there's electricity, there's magnetism around the electricity. And of course, magnetism itself creates electricity. So you've got electricity and magnetism and electricity, and the Birkeland currents tend to form in a circular form, and the electric universe people say that it causes double insulation, it protects itself. And some of these Birkeland currents can be light years across, they're huge, right? When they get really powerful, you get light, they start to light up. And it's glitches in these which they think causes the formation of bodies and stars.
So how would that actually work, Piers? Do you know anything about this?
Yeah. I used to do galaxy formation, and I did an MSc on a project involving galaxy formation and expansion of the universe, and a whole number of things. The straightforward gravitation model for explaining irregularities in the universe and the formation of galaxies themselves, and even the details of galaxies. Trying to rely on gravity alone is problematic. There are a lot of ways of playing around with it, but it is definitely problematic. And the electric universe, a general idea, basically says, well, okay, electric forces give you more and more opportunities, and that is absolutely true, if you can understand them, that is. And I think, it is very important to be clear, first of all, in deep space, there is not neutral stuff around. There's positive charges, negative charges, and forming what Steve mentioned earlier, plasma. Whereas on Earth at home, there's positive and negative charges, but generally speaking, all of them are stuck together, and you have neutral objects. Like this book is it might have a tiny surface charge, but basically the body of the book is neutral.
Yeah, right.
But if that book was broken up into all its atomic bits in space, then all the atomic bits would be positive and negative charges flying around, which is the plasma. So what happens in space must mean that electrical and magnetic forces are going to be much more important. So I agree with the general view that you have to move into that sphere a lot more in order to understand it. Now, the Birkeland currents are a very interesting idea. I don't quite understand how they all work in detail, but the basic idea is that there's communications, if you like, or conveyor belts of particles and fields and so forth between stars, through galaxies and so on, and these can help explain you get line structures of galaxies, all sorts of structures of groups of galaxies, which in galaxy formation theory are quite difficult to understand, because you have clusters and you've got clusters of clusters, but it's not as simple as that. You've got lines of galaxies, all sorts of things are going on, which, as Steve says, appear to be better explained by an electrical approach.
Yeah. In deep space, the temperature is not absolute zero. It's 3 degrees above absolute zero. And also in deep space, there is background radiation. So, for example, in deep space, in a cubic meter of deep space, there's 1 million charges. There's 1 million pieces of matter which are all electrically charged. And I think that this is actually what that conducts electricity. I mean, if you think about it, I know it takes a good telescope, but if we can see objects in space which are 10 billion light years away, that light must be transferred by some medium. Originally they called it ether, but that's not sufficient for modern day scientists. But as soon as the background radiation discovered, the astrophysicists jumped on it and said, well, this is the evidence of the Big Bang. But it's not. It's actually the basic nature of matter.
Yeah, I mean, the explanation that the Big Bang happened so long ago, and it's still that it can still be heard, and it's basically still there in some form as a background noise. I always found that rather a childish idea, really.
Yeah, it's odd. Yeah,
it doesn't really work.
I'll tell you another thing about the Big Bang, is they always say, yes, it always seems like we were where it started. So suddenly we're the centre of the universe again, because you look at it, it's all expanding the same way. Now they get round this and saying, yes, if you think about a balloon, if you blow up the surface of a balloon, all the distance get increased. But that is a balloon. Try and do it in 3 dimensions, and it becomes a lot more problematic. So, I don't know if you'd describe me as a religious man, but I believe that the universe, the space, is eternal, but everything in it has a life.
I think that's a really good way of putting it, and I would kind of agree with that on a philosophical level. The idea that everything came out of one incident, and the way that we're told that life on Earth was created is for very childish minds, in my opinion. And I'm not a scientist, but having looked at this stuff, it fits with a control model, in other words, a religious model that we need to be kept from the knowledge that we could be infinite.
That's right, yeah. Well, the whole effect of the Bible goes very deep, especially into American culture. First thing they saw when they were in orbit and they saw the Earth from space, they started to quote the Bible.
Yeah, of course, because this is what we have to keep reiterating to keep all this stuff in its place, so that we don't look into it. But it's been a very interesting discussion today, and would you like to make any comments on what Steve's just been saying?
Yes, well, there's many things one could say. But I agree that the Big Bang idea is like it's a projection of observations or assumed observations, and from that you conclude it started from somewhere. But there's other ideas saying an oscillating universe expands and contracts and so on, you see. So you don't ever get a actual bang, you get a smaller volume and then it all expands again. Or the other idea is a basic steady state idea, i.e. what we're seeing in fact is continuous creation of particles and disappearing of particles, which was Hoyle's idea of the universe. But there are, I would like to point out, some really quite serious problems of the expanding universe Big Bang theory in its own terms, because the theory says, okay, if you have this thing that explodes, then disuniformities in the beginning of it will form disuniformities later on around which galaxies can form, right? However, the universe as you look at is much too uniform than they expect. So, because the way the theory says it expanded, it would have had enough time to form all sorts of irregularities and lumps, but they're not seen there. It's very homogeneous. There are tiny irregularities, right? Now, they get these out of the way by saying, oh, well, in the early universe, it actually expanded at much faster than the speed of light. Well, okay.
Oh, yeah.
Oh, yeah, we
I
slowed
like
down,
that.
doesn't it? That's right.
But you see, the other tenets of standard physics is that the speed of light is fixed, you see. So you can't have it both ways.
That's
but
a really
nevertheless,
good point.
it is in there, and you have to have this superluminal universe to explain the uniformity. Now, there's other people who say, well, the disuniformity comes from something else altogether, and that what we're seeing is actually an error of observation. And I've been to electric universe conferences where some of this stuff has been put forward.
Welcome back to Windows on the World. We're talking about the electric universe, and in particular in this section we're going to be talking about dark matter and what it really is. So welcome back.
Okay, well, the idea of dark matter was first introduced in the theory of galaxy formation, which I did a lot of work on when I was studying astrophysics as an MSc in Queen Mary College, and published various papers on the matter. The point is, the fact that galaxies are there suggests, if it's a gravitational force holding them together, there has to be enough mass in there to have all the bits of the galaxy staying around for long enough for them to be seen now, and not having either collapsed or actually just expanded, because the parts of them move too fast by themselves to be held together, so it seems, by the separate parts under gravity. Therefore, dark matter is introduced as something which you can't see, which is in all galaxies. Right. Now, the idea was then introduced that they...
So for people who don't know what neutrinos are, can you explain that?
Neutrinos are very light neutral particles which are needed in atomic theory to explain and understand radioactive decay, for example, and many other things. And the universe, under modern theories, and probably all theories, is full of neutrinos. They go through you all the time. There's about one neutrino in every cubic centimetre of space, and they're no problem. And they interact with anything very, 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 very rarely. But they nevertheless will have, if they're not massless, they will have a small or big enough gravitational field to potentially allow galaxies to form around this dark matter. So that is one potential source of dark matter. Then there's a whole lot of theories that we must have the dark matter, and we're looking around for the source of dark matter. And the neutrino theory is out of fashion now, and there's other ones. So that's the dark matter issue. Then we have the dark energy issue, which gets mixed up with them, namely that because the universe is expanding and appears to be expanding at a greater rate further out you go, or something like that. I mean, it's expanding and possibly at an increasing rate. The idea is you have a dark energy in the universe that is being released all the time out of what we think of as nothing, and that dark energy sort of drives expansion. They're different things and neither well understood, and may both of them be essentially mathematical games in order to explain things we don't understand.
Yeah, we're quite familiar with those sort of things, models, projections, and that kind of.
I'm not saying they are or not,
things.
because they're
Well, we don't
very
know, do we?
interesting stuff.
No.
But obviously, there are many things we don't know. But again, the electric universe theory says, well, yeah, but hang on, what about all the positive and negatives and charge separations, which permeate the whole universe, 99% of which is plasma, i.e., positive and negative charges which are separated.
So that brings us back into what we were talking about to start with. Do you want to come back in there, Steve?
Right. Well, I'd like to say a few things about the sun. Is the sun is being described as a fairly typical star, so if we could understand the sun, we'd understand a lot about the universe. But what interests me particularly is the heliosphere, which is this massive electrical field that embraces the whole solar system, which comes from the sun. And we know it's electrical because what they call the solar wind accelerates the further out you get, and you only get that effect with electricity. And when you get to the edge of the solar system, which Pioneer and Explorer spacecraft have done, the astronomers were astonished to find these craft slowed down as they exited the solar system. And they've now discovered that that is actually because there's actually a field of plasma, positively charged plasma, outside, which presumably the heliosphere is protecting us from, pushing it out. And this is actually, at one point, they thought that these spacecraft were actually going to slow down completely. But so this shows how the sun is related to the rest of the galaxy. And the sun, where we're all travelling at 500,000 miles an hour around the galaxy, this must be affecting the energy. But the immense amount of energy the sun's putting out, we don't know where it comes from, because the electric universe people don't believe there's any nuclear reactor in the middle of the sun, because actually it's not the hottest part. On the surface of the sun, which is 5,000 degrees, it's not hot enough to create nuclear fusion. But there is a very hot part called the corona, several thousand miles above, which is 15, 20 million degrees, which could create fusion. But these things, the electric universe movement doesn't have the facilities to be able to research these things, and since the astronomical establishment is not really accepting it, it's still open season.
We covered that on a previous show, and what the sun is, how it functions, and how it may function very differently from the way we're led to believe. That the surface is hot, but the actual planet itself isn't.
Right.
That is a theory that's been around for quite some time. So is that something that you agree or disagree with, Piers?
Well, yeah, what Steve says is very interesting, and quite a lot of important things there. First of all, about the heliosphere, and it is important to understand what it's about. People know on Earth we have a magnetosphere, where the magnetic field of the sun protects us from the solar wind, and the solar wind itself is what's, as he says, called the heliosphere. So around the Earth, we have the Earth's magnetic field, which keeps it out, right? Now, the sun, though, of course, has got its own magnetic field, and that magnetic field then extends along with this heliosphere. And if you like, the Earth is bathed in an extension of the solar corona. It is still part of the solar corona, but it reaches an edge.
Yeah.
It reaches an edge where the solar wind basically bumps into other winds in this very tenuous plasma in the galaxy. And between galaxies, of course, there's going to be other winds. So we have what's called the heliopause down there. out there where the solar wind basically, or the magnetic effect of the sun is limited, you see. Now the motion of the spacecraft which exited the heliopause are, if that's the right word for it, I think it is the right word for it. There's all sorts of things you could think about. See, the craft could well have got an electric charge on it, which will, if there's something else electric charge, will affect its orbit a bit. I mean, I don't know what the arguments are for and against as to explanations as to why its speed wasn't quite what it was, but it is nevertheless pretty important.
So
the thing about the temperature of the solar corona. Now, there are standard theories actually which say, but they are contentious standard theories, which say, yes, the high temperature in the solar corona is caused by magnetic reconnection of magnetic fields, right? Now, but frankly, if you look into the supposed mechanisms of this, I would describe them as nonsense. And I was quite convinced at the Electric Universe conference where it was pointed out that way of looking at it is nonsense. But the fact that the corona is very hot could be all sorts of electrical or even nuclear effects going on, which we don't fully understand. Now, I know there's an argument saying, oh yes, okay, maybe the centre of the sun doesn't have a nuclear reaction. But all I can say is it's pretty likely there is one there, just because of all this compression and therefore ability to react. So I don't accept that it's proven there isn't one. I'm more likely in favour of there is nuclear fusion going on. But there are, to be fair, really interesting ideas about what could be a completely different view of it, an electrical structure of some sort in there. And that, again, is going to be discussed on September the 8th and 9th at this conference on the new dawn of truth.
Yeah, which we're all looking forward to. So, Steve, would you just like to come back in there? Because we've been talking about the sun particularly, and we were going to talk about other planets as well. Is there anything you'd like to add to?
Well, the only thing we haven't mentioned is comets. Comets, because comets do actually travel outside
very long way,
the heliopause, right?
Yeah.
Some of them we don't know how far they go because they lose contact with them. But out there, of course, there's a different charge, and when the comets pan back in, they start to light up because of the charge that they're getting from the sun. And actually, if you look at comets, they're only a few miles across. Even Halley's comet's only about 8 miles across, and it's just a bit of rock. You wouldn't be able to see it, except for this incredible light that comes from travelling in towards the sun. And the other interesting thing is that comets have tails, but it's not like a vapor trail where they come from. It's actually a trail out along the line of the solar wind. So whether it's particles off the comets or whether it's charge, we don't know. I'm inclined to think that it's just electrical charge, because these comets are so small. If they're particles that come up, they thousands or millions of years been travelling, there wouldn't be any of them left. But they certainly aren't dirty snowballs, which was the official theory that was carried. In fact, when Comet Tempel 1 was landed on by its probe, they put they thought there was ice there, and they put their ice picks down, but there wasn't any ice, and it knocked him out back into space. And it took several hours for it to settle down with the gravity.
Yeah, it's very interesting, because that takes us into the other areas of ancient mythology, which we can't get into today.
Exactly.
But would you just like to?
Yeah, no, I think what Steve says is very important. I mean, well, everyone wants to explain everything, and of course the explanation for what comets are was an oversimplification. Yeah. But it's very easy to understand, what he says about the trails, because a comet, the tail, as it's called, misnomer, always points away from the sun, i.e. it is something to do with the solar wind. And the point about if it's material coming off the comet, it would eventually, it wouldn't be any comet left. Well, that kind of works, but the basic theory is that it only shows these tails when it is near the sun, because that's when the solar wind is less dense, more dense, and therefore having an impact. So further out, there wouldn't be any tail or loss of stuff when it's at the heliopause. But you know, I said calculations could be done, and you could estimate, well, okay, in the life of the comet, how much of its mass is going to be left when it comes around again,
right.
which is a fair thing to calculate, and I'd like to see such a calculation.
Well, I think we should really. This is something we can carry on with, and this conference is going to be very interesting by the sound of it on the 8th and 9th of September. So is there anything you'd just like to say in conclusion, Steve?
I think we've covered a lot of areas. It's been a pleasure to go through these issues with Piers, and I think maybe when this is out, we might be able to come back and cover some more issues.
I think we should. I think we should focus on some of the detail next time. We've had quite a good overview, and I've actually put things together today that I hadn't necessarily put together with some of the electric universe stuff that's on the internet that I've been watching and over the last couple of years. So I think it's been a very good introduction. So thanks, Piers, thanks, Steve, and that's it from Winners on the World, and we'll see you very soon.
Thank you.